Hello, everyone. Thank you for the introduction. So, my name is Cor, and I'm a PhD student from the University of Bristol. And my the presentation today is on stress corrosion cracking with a corrosion small punch test setup. So, I'm in my third year of my PhD, and I'm working with the National Nuclear Lab of the UK. A bit background on the topic is that in the UK, the advanced gas-cooled reactors are in most of them are in the decommissioning stage, and the spent fuel is stored in a cooling pond in Sellafield, and the fuel cladding of the nuclear fuel is also stored in the cooling pond, and but then they're made of special. They're made of specially made designed stainless steel, but the issue is that some of them may develop stress corrosion cracking while stored in the pond. So in my PhD, I wanted to develop a new small punch test setup to study the behavior and monitor the stress corrosion cracking of AGR fuel cladding with a surrogate 304 stainless steel material. And also I wanted to use digital image correlation to observe stress corrosion cracking. So some background stress corrosion cracking is that is caused by the combination of susceptible materials, mechanical driving force, and a corrosive environment. This is an image of a typical stress corrosion crack. Some background on small punch test. So this is a schematic of how a small punch test works. So the specimen is placed between two dies, and it is punched by the top punch, and there's it is deforming in the die. So it is method that is commonly used in the nuclear industry because it only requires a small sample size, and this is a load and deflection diagram of a small punch test. And one of my previous colleagues from our group designed this setup. So he designed a mirror. He placed a mirror below the small punch test to enable DIC monitoring of the specimen from below. And apart from the implementation of DIC, the small punch test can also be used with in situ testing as well. So in my setup, I wanted to develop a corrosive environment in the small punch test setup to be able to develop stress corrosion cracks in situ. So this is my setup. So it's modified from the previous design. Apart from the DIC below, I introduced a channel in the lower specimen holder that can allow a flow of a corrosive solution. And then there are also two auxiliary holes that can be used for thermocouples and other equipment. And so this is where the specimen is placed. The load is applied through the punch to a ceramic ball that is causing deflection on the specimen, and it is also sealed by some O-rings, and the DIC is placed below. There's an observation window below the specimen holder, and this is how the new setup looks. And so the load is applied by a benchtop Phoenix hydraulic machine. The load can be up to 10 kilonewtons, and these are the connectors for the corrosive solution. And this is so I introduced a corrosive loop in the small punch test that can allow the initiation of stress corrosion cracking. So the solution is placed in a heating bath here and is pumped by a small pump into the testing rig. So I did some initial trial tests to find what solution I can use to allow stress corrosion cracking. So initially, I used some thermally sensitized 304 stainless steel, and in this one is a small self-loading tensile rig. It was placed in a solution, 1000 ppm sodium thiosulfate solution with some hydrochloride solution. I was heated to about 80 degrees, and stress corrosion cracks successfully developed in 7 hours. But then, as you can see, because of the presence of hydrochloride, and I wanted to use the DIC to monitor it, the chloride is causing quite a lot of corrosive products. So in my small punch test, I removed the chloride with only sodium thiosulfate. And also I did some trial tests on the small punch test, the loading itself without any solution. So this is one of my specimen, and was loaded to fail. It failed at about 2.5 kilonewtons, and I chose to load it at about 1.5 kilonewtons for the corrosive small punch test. So this is how the whole setup looks. A specimen was placed in the rig, and in my first corrosive test, I only chose to have quite low solution, quite low concentration for the solution, and I was only loaded for 6.5 hours. And this is how the sample looks afterwards. And under an optical microscope, you can see there's a crack-like deformation on the top of the surface, specimen surface. But then when I put it in the SEM, it looks relatively, it doesn't look like a crack on the surface. So I improved the test to make this stress corrosion crack happen. So I changed the solution to 1000 ppm again, and after 70 hours, as you can see, there's still some deformation, but there isn't any stress corrosion cracking happening. And I continued this experiment for another 40 hours, and it was actually done quite recently. And unfortunately, because of the security clearance issue, I didn't manage to clear my image for this presentation, so I have to describe it verbally to you. But then, yeah, in the end, I managed to initiate some stress corrosion cracks after 113 hours. And most of them, they are intergranular cracking along the grain boundaries, and the length of them is about 20 micrometers. And there are also some corrosive voids initiated on the specimen as well. So for my next step, yes, to conclude first, is that my setup can allow stress corrosion cracking to happen for a 304 stainless steel after 113 hours. And in the next step, I'm planning to use the DIC on the system So I will be able to monitor the cracks happening in real time. And also, there's one thing I want to change is because you can see on those specimens, you can see there's quite a severe deformation on the surface, and it's rather difficult to tell if there are ionic cracks or not due to those deformation. So I think for my future experiment, I'm going to change the loading to only elastic region, because I think for stretch Trojan cracking, elastic stresses is enough to allow the initiation, and I think it will be easier to monitor the specimen with DIC if I just stay in the elastic region. And thank you for your attention. Are there any questions?